Welcome to the video 2 of our software architecture series. Here we will learn about the architectural decisions that decide your fate. So friends, projects rarely die because of curly braces or any code error. They die because of early design decisions. There is a famous writer, Ian Woods. He says, software architecture is the set of decisions which, if made wrong, can completely cancel your project. So, in this lesson, I'll show you the decisions that matter most, how they control quality, cost, schedule, and team structure, and how to use them to move from a developer to an architect role. So, the first point is the decision layer. What architecture really is. Architecture is not a box and line picture or a framework logo. Architecture is a small set of early, hard to change design decisions which you have taken for your project. These decisions constrain everything that comes later: design details, code implementations, integrations, deployments. They also enable or inhibit your driving quality attributes. We learned about quality attributes in the previous video. You can check out that video as well. For example, they drive performance, they drive availability, security, scalability, modifiability. When the architecture is documented, everyone uses the same map and the same words and the same terminology. That shared map lets you, as the architect and the project manager, reason about the cost, the schedule upfrontly before even kicking off things. It also supports and evolutionary prototyping. Basically, you can build small prototypes to decide whether this design choice or this technology choice will work for me or not. So you build a thin working skeleton and then continuously, iteratively grow it safely continue to grow it. So the second point is architecture is also a people system. Architecture and organization mirror each other. Sometimes the design dictates how teams are split. Sometimes the organization of teams forces the design. A good architecture becomes a transferable model for a complete product line. It focuses on assembling components rather than reinventing them. By restricting design options at the top, it channels the creativity where it matters and keeps complexity of the system under control. It also becomes the best training map for onboarding a new engineer. Now the third point is quality of the software doesn't happen by accident. Whether your system shows the qualities you want, it largely is determined by the architecture. But architecture alone cannot guarantee quality. It is also driven by implementation and your deployment choices. So, as a good architect, it is necessary but not sufficient. You need the big picture and you need the details. So, some of the concrete architectural strategies you can apply today are modifiability, which means give each element one clear responsibility and aim for common changes to touch one element or a very few. Second is security. Protect every interaction between elements. Control access, add specialized components like authorization and audit. Third is scalability. Localize resource use behind stable interfaces so you can swap in higher capacity parts later. Avoid hard coded limits. The fourth is incremental delivery. Manage intercomponent usage so you can ship subset features without breaking the rest of the system. Another one is reusability. So keep coupling low so components can be extracted without dragging half of the system out. Now the fourth point is where the money really goes. Design, you have to design for change. About 80% of the total cost arrives after the first release. That's maintenance, growth, support. So we design our system to keep changes cheap. Every architect sorts changes into three types. Local change, which means it affects one element only. Example, a new pricing rule inside the pricing module. Second is non-local change. Several elements, same architectural style. Example, pricing rule plus DB plus fields. Third is architectural change. You're changing how elements interact with each other. For example, whether it is client to server or it is peer to peer. A strong architecture makes common changes local. That's the goal. So, what is the architect's job during change? An architect's job is decide which changes are essential, then choose a low risk path to achieve those changes. Then assess the impact and order the sequence and priority of the changes. For this, an architect should have a wide view of dependencies, performance, runtime behaviors across the system. So, the next point is an architect should be able to predict and evaluate early. Architecture gives qualities in predictable ways when you choose known tactics and patterns. That's why we can predict quality early by evaluating the architecture before the full code has come into picture. Like any mature engineering field, analysis is the norm. The earlier you find a design problem, the cheaper it is and the safer it is to fix. So the next point is architecture is also a shared language. Architecture is a common abstraction most stakeholders can understand with a little bit of coaching. It's simple enough for non-technical people, yet detailed enough to guide the implementation engineers, integration engineers, testers, and the guys deploying. All the stakeholders should connect to the architecture. For example, user wants fast, reliable, available system. Customer wants things on schedule and on budget. Managers want team to work independently with disciplined contracts and boundaries. So an architect chooses strategies to satisfy all of the above. This language lets us express, negotiate and resolve concerns early, even in large systems. User may not see the architecture, but they feel it in responsiveness, in its uptime, in its security, in its safety. Now let's talk about the early design catalog. Architecture is the first point where the big design decisions can be scrutinized. The early bindings carry enormous weight and changing them creates a ripple effect. So these decisions should be decided deliberately. For example, deployment style, single processor or distributed system. For example, layers. Will it be a layered structure? How many layers will be there? And what will belong to what layer? Or for example, communication. Whether we'll go for a synchronous communication or asynchronous. Whether we'll pass control, whether we'll pass data or we'll pass both. Again, for example, platform dependencies. Should you rely on the operating system hardware features or should you build an abstraction layer? Again, for example, security posture, encryption in the transit or just at the rest. For example, operating system, which operating system to use or what network protocols to use. So changing any one of these in mid project touches the code, tests that are written, the infrastructure, the staffing, the team management, the schedule, it impacts everything. So let's talk about conformance. When code truly exhibits the architecture. An implementation exhibits its architecture only if it conforms to the architectural decisions. For example, we implemented the prescribed elements, modules, services, data stores. These elements interact using the prescribed connectors, REST APIs, message brokers, queues, etc. Whatever we prescribe. And each element fulfills its responsibility to the other. These are some of the constraints on the implementers. They are not just suggestions, they are a constraint. I don't need to be the best programmer to be the architect, but I must establish, analyze, enforce the architectural trade off of all these decisions that I've taken. So as a viewer, you must be wondering, I'm a software engineer, how can I grow into and software architect? So here is your practical blueprint. Here's the path I use and the path I teach to developers who want to become architects. First one is pick driving qualities of your system, maybe top 2, 3 or 4. Then choose tactics that match those qualities. For example, if you want modifiability, you should set up clear responsibilities, you should set up stable interfaces. For example, if you want security, you should build protected connectors and authorization components. If you want scalability, you should isolate resource use, avoid hard coded limits. If you want incremental delivery, you should manage inter-component usage. If you want reuse, you should go for low coupling. Now, these were some examples. The third point is you should write down or document early design decisions. For example, layers, whether you're going for sync communication or async communication, what kind of protocols you are using, what platform dependencies you are using, what encryption you are using, what deployment style you are using, and keep it short and keep it visible. Then you should go to build a skeletal system that exercises these real communication paths. Then you should evaluate with scenarios. For example, you should evaluate with a performance failure or an abrupt change request. You should learn to adjust when you know it is cheap. Then you should align your teams to structures which you have decided so that work is independent and interfaces are clean. You should also plan cost and schedule for the architecture. For example, you can parallelize some chunks which can be built independently. You should give high priority to the critical path where you need some specialist engineers to implement it. Then the next point is you should set conformance checks in reviews so that the code stays aligned with your architecture. Then you should capture the model for reuse if you're building a product line which will be enhanced. So friends, these were the points that I wanted to talk about in this video. So as a viewer, what is your next step? What you should do? I'll try to summarize what I talked about in this video. So friends, architecture is a small set of early high impact decisions that decide your fate. Use them to localize your change, secure communication, scale by isolating resources, ship incrementally by managing dependencies, and reuse with low coupling. Do this, and your control, quality, cost, and schedule will be on track. So, as a homework for you, write your project's 5 early design decisions. Now, for each decision, note the quality that it affects. Also, note the risk if it goes wrong. And one test or prototype you will run this week, write about that as well. So, friends, in the next video, we'll talk about how can you turn quality into scenarios and measurable requirements. I hope you liked our video, you liked the content, you liked the presentation. I've been putting a lot of efforts to bring the best video to you and the best content to you. Please show your love, please show your support by liking this video, sharing it more and more so that I get the reach that I expect for all the efforts that I put to create this kind of content. Please show your love, please show your support, and keep watching SPS Tech.